So 5-1 talks about special segments in triangles. So I want you to draw a segment and make sure, it doesn't have to be normally, but for our purposes here, I want you to make sure that it's a horizontal line. So, and make it a fairly large horizontal line. This is going to be points A and points B. And connect those two. So that's two vertices of our triangle. The third vertex, I do not want you to make this into a right triangle. That doesn't mean that these special segments aren't in a right triangle, but they won't look the same if you make it a right triangle. I don't want you to make it isosceles, definitely not equilateral. So I want you to put the third vertex off center to the right. Name that C. And then finish off the triangle. Now that's not to say again that equilateral, isosceles, or right triangles don't have these same segments. They just look different. And in your homework tonight, you're going to explore how they look different in various triangles. But I don't have time to write all those down. That's your job. All right, so name this picture special segments of a triangle. We are going to have quite a few definitions and theorems associated with these special segments. Your job is to focus on the similarities and differences between those segments. And there's 4 segments that we're going to look at, 3 of which we're putting on this picture. The 4th we'll just talk about. So the first segment, I want you to count how wide your segment is from A to B. It's probably different than mine, but I want you to count the number of boxes that are there because we're going to put a midpoint. You need to find the midpoint of your segment AB. So mine is 2, 4, 6, 8, 10, 12, 14. Fortunately, mine's an even number. What's 14 divided by 2? 7. So I'm going to go over 7. Now, if yours were 13, what would your midpoint be? 6.5 or 6.5. So you would put your midpoint between grid lines. So find your midpoint, and I want you to label it M as in Mary. The first segment is called the perpendicular bisector. Now, if something's perpendicular, what does that tell you? They're at right angles. So the 2 segments are going to make right angles. If it's a bisector, what does it do? It cuts a segment into 2 equal pieces. Does it make sense that I found the midpoint of segment AB? Because I'm going to use a perpendicular bisector on segment AB. So there's our midpoint. The other part to a perpendicular bisector is that it is perpendicular. So please draw a perpendicular line, dot it, through M. And notice I extended outside the triangle because it could. Put a perpendicular marker here. And then this point where it hits AC, call that P as in Paul because I like the letter P. I don't know, just because. So let's define what a perpendicular bisector is. And I'm color coding this for a very good reason. Oh, put a little arrow here. Perpendicular bisector. All right, so let's define that puppy. Oh, my pen has disappeared. Hang tight. All right. So a perpendicular bisector is a line or segment that passes through please let them in the midpoint of a side of a triangle and is perpendicular to that side. So notice that our perpendicular bisector happens to be a line or a segment. The segment would be from P to M. This line continues infinitely if you put arrows on it. That passes through the midpoint of the side of the triangle that it's bisecting, and it's perpendicular to it. So those are the two characteristics. It has to be perpendicular to the side it's bisecting, and it has to cut that side into two equal pieces. How many sides are there to a triangle? 3. So couldn't I have drawn a perpendicular bisector through CB at its midpoint, and one through AC at its midpoint? Interestingly enough, all 3 of those are going to intersect at exactly the same point inside the triangle. And I would like you to go to your textbook tonight and look at those pictures, because they're going to do a picture for each one of the types of segments that shows you those 3 things intersecting. I want you to see what they look like, because you'll have some questions related to that on your test as well as in your homework. And since there's 3 sides, every triangle has 3 of these. All right, there are 2 theorems associated with a perpendicular bisector. The first theorem is theorem 5-1. Again, do not memorize the theorem number, but what it says. And it essentially says any point on the perpendicular bisector of a segment is equidistant equidistant means equal distance from the endpoints of the segment. So again, it says any point on the perpendicular bisector is equal distance from the endpoints of the segment that it's bisecting. For instance, let's say that isn't point P on this perpendicular bisector? And I could have chosen any point. I could have chosen that point right there in the very center. I could choose a point outside of the triangle as well. Doesn't matter what point I choose. This point is going to be the same distance from P to A as it is from P to B. And if I were to draw a line going from P to B and from P to A, I would have an isosceles triangle. And so let's measure. I'm going to prove it to you. So if I measure the distance from A to P, well, of course the glare is on there. Let's move it down. All right, isn't it about, a little more than 1 3/4 of an inch? Okay. It's 2 hash marks away, or 2/16, 1/8 of away from 2, correct? So let's measure that distance from P to B. Let's get my stuff out of the way. So from P to B, let's move it out of the glare. All right. Whoop. So if that's 2 right there, isn't it exactly the same distance away? It's 2/16 or 1/8 away from 2 on there. Aren't they exactly the same distance? So isn't point P equal distance from these endpoints? Yes or no? Yeah. And I could do the same thing for that point right there. If I measured from A to that point and from that point to B, it'd be a different distance, but it'd be the same for both sides. And that's all that it's saying. The second theorem associated with this is essentially going to be the converse of what you just read. Look at how similar the language is. Theorem 5-2. Any points equidistant from the endpoints of a segment lies on the perpendicular bisector. I guess you could say of the segment. So it says that if you find a point and it's equal distance from the endpoints of a segment, then that point must lie on the perpendicular bisector. Where the other one says if you have a point on the perpendicular bisector, then it's equal distance from the two endpoints of the segment. Aren't they converses of each other? Yeah. So if you know one, don't you know the other? Essentially. All right. Y'all need to be taking vitamin C and eating all of your fruits and vegetables. You sound terrible. All of you in general, not just you specifically. All right. The next segment is going to be called the median. This is also new to you, so take your picture. And I want you to draw a segment that goes from the vertex C to point M. And draw an arrow here indicating that it is called the median. Median. How is it similar to the perpendicular bisector? It what? Or it ends at the M. What's M to the side? Isn't AB, segment AB, the side opposite angle C? All right, so notice that our medium, good Lord. Notice that that median ends at the side opposite at the midpoint of that segment, right? Is it perpendicular to that line segment? No, does not have to be, okay? But what it does do is it has to come from a vertex and it has to go to the opposite side's midpoint. Those are the two characteristics. Whereas the two characteristics of the perpendicular bisector was that it intersected the midpoint of a side of the triangle and it's perpendicular to it. Could the perpendicular bisector and the median be exactly the same line? It's possible. If your triangle is an equilateral triangle or an isosceles triangle, it could be. And you're going to explore some of those possibilities today in your homework. All right, so let's write down the definition of a median. So in all of these segments, you're looking for the two characteristics that make it special. All right, a segment. Median is a segment. Notice it's not a segment or a line, it's a segment that connects a vertex. Bless you. You sound like a bunch of old people in church. You ever heard the hacking and coughing and sneezing that goes on in church? That's what you all sound like today. A segment that connects a vertex of a triangle to the midpoint of the side opposite that vertex. How many vertices are in a triangle? 3. So doesn't every triangle have 3 medians? Yes. Where do you think the 3 medians intersect? Nope. All in the same spot. All 3 medians will intersect at the same point inside the triangle. Again, I want you to look at the picture that's in your textbook so you see it. Every triangle has 3 of these. All right, the next one. All right, the next one is called the altitude. The altitude of a triangle is another name for what? This you know. Height. And we've talked about this before, okay? Basically, if you're going to have your height measured, you go to the doctor and you have your height measured, are you going to measure this way? No. And I'm slumped over, and I don't want to be on camera. So I'm slumped over, right? We don't ever measure our height that way. No matter if you're short or tall. If you're tall, most of us who are tall are very proud of our height. Girls, if you're tall, you should be very proud of that height. Trust me, you'll find a boy that's taller than you someday. All right, so when I measure my height at the doctor's office, I'm perpendicular to the floor, right? If you're short, you're like stretching as tall as possible to get as many inches out of your height as possible, right? So tall people tend to be proud of their heights, whereas short people are trying to get as much out of their height as possible. Nobody slouches or should not be slouching when you get your height measured, right? Same thing in a triangle. However, it's possible, especially in an obtuse triangle, that if I'm going to go from C to a perpendicular distance to the side opposite it, isn't that my altitude? Is it possible in an obtuse triangle that it might not be inside the triangle? Do you remember doing heights or altitudes in figures in a chapter many moons ago? Remember where we did the distance from a point to a line? And sometimes from the point to a line was in a figure like a triangle or a hexagon or something like that. Remember how you might have had to extend that line in order to make that distance from that point to the line perpendicular? I'll show you one in just a minute. Label this one the altitude. And in parentheses you can put height so that you recall that, oh yeah, it's supposed to be from a vertex, here's the two characteristics, from a vertex to the side opposite, wherever it hits, so that it's perpendicular. Could the altitude, the median, and the perpendicular bisector be one and the same? Absolutely. What if I took, I'm going to turn this triangle, and I want to find the altitude, oops, let's move that up. I want to find the altitude from A to the side opposite. Isn't the side opposite A, B, C? Would you agree? If I want my height or my altitude to be perpendicular, wouldn't I have to put my ruler so it's flush against the bottom here? Isn't that a perpendicular line now, the edge of my ruler here? Watch as I connect it to A. I'm going to get this ruler to that point. There's the end of my line. Have I hit A yet? No. Don't I have to keep extending this line out and out until finally I hit A? Do you see how this is now, oops, I'm off kilter just a smidge. Do you see how now it's perpendicular to the side opposite, and now I can connect it to A? But look at where the endpoint of that altitude is. Isn't it outside the triangle? Wouldn't I have to extend this line out here to make a perpendicular line from A to the side opposite? All right, so this is different than the median and the perpendicular bisector, because your altitude might be outside the triangle. All right, so look at how the definition is slightly different. So let's write it down. Altitude. All right, an altitude has one endpoint. Oops, let's spell endpoint correctly. At a vertex of a triangle, and the other on the line that contains the side opposite that vertex. We're not done with this definition, but I want to stop right there for a minute. Notice the change in wording. It says it has one point at the vertex and the other on the line that contains the side opposite of that vertex. Isn't this side opposite of a triangle a line segment? When I extend that line segment out longer, if I need to, isn't that line segment part of a longer line? That's why the wording is slightly different, because if you have to extend that side opposite in your triangle, you've now created something different than what the original triangle was. And so we're only concerned with making a perpendicular distance from that vertex to the line that contains the side opposite. So it's no different than finding the distance from a point to a line. And so the rest of it is so that the segment is perpendicular to this line. And how many vertices does a triangle have again? 3. So couldn't I draw 3 altitudes? Every triangle has 3 of these. Where might the 3 altitudes intersect? Again, they're going to intersect in exactly the same point, all 3 of them. Where might they intersect? This is the only one where they can intersect both inside the triangle, outside the triangle, or on the triangle. And again, you're going to explore that in your homework. Again, I ask you to look in the teaching pages of your textbook prior to doing your homework. They show you all 3 of those pictures where they intersect inside, outside, and on. All right, the 4th one, I'm going to flip the page because we're not going to actually draw it on here. But the 4th one deals with an angle bisector. And so, what do you think an angle bisector does? It bisects an angle. So let's say that this angle right here, angle A, you don't have to draw this in, is 20 degrees. If I drew a line in there that would bisect angle A, what does it do? It creates what? 2 equal angles. So what are my angles going to equal? 10. So it would look, and mind you, I'm eyeballing this. Let's see if I can eyeball it fairly decently. Oops, I went down. But that pretty much bisects it into 2 equal angles, doesn't it? 10 and 10. One of the theorems that's going to be associated with this, basically the angle bisector is going to go from a vertex to somewhere in the triangle so that it cuts that angle into 2 equal parts. But remember the perpendicular bisector? Remember the theorems that went along with that? Didn't the theorem of this say that any point on the perpendicular bisector was equal distance from the endpoints of the segment? You're going to see 2 theorems associated with the angle bisector also that are similar to that. If I chose any point on that angle bisector, the theorem is going to say, remember, the distance from a point to a line is always perpendicular. So it's going to be the same distance. These distances here are going to be equal. So any point on the, and you'll write this down in a minute, but any point on the angle bisector is equal distance to the sides of the original angle that it bisected. So I could choose any point here. So this point here, the distance from a point to a line is perpendicular. These, again, would be the same distance. Not the same as this distance, different, but still the same. Does that make sense? So the angle bisector has something in common with the perpendicular bisector. And here we go. You ready? No? Do you hear no? Well, you need to be. All right. Here we go. Last definition. Angle bisector. Shh. Last of the special segments. Angle bisector is a segment that bisects an angle of the triangle and has one endpoint at a vertex of the triangle and the other endpoint at another point on the triangle. It's not necessarily going to hit the opposite side of the triangle or the vertex or the angle that it's cutting in half, but it's going to hit somewhere on the triangle. It can be wherever. All right, here are your 2 theorems associated with this. Theorem 5.3. And you'll notice that these are converses of each other also. All right, so Theorem 5.3 says any point, and this is what I just explained, on the bisector of an angle is equidistant from the sides of the angle. Remember, the sides of that angle are two sides of the triangle that create that vertex that you are bisecting. The second theorem is your converse. Does that have a person's name on it, Caleb?
No.
Are you sure? Because I didn't want you taking that box, because that's, people are going to use that for an extra credit thing.
For sure.
So go get one from the back. Is there one up there in the back at all? All right, well, too late, he's touched it now. All right, Theorem 5.4 says any point on or in the interior of an angle and is equidistant from the sides of an angle lies on the bisector of the angle. So they're just converses of each other. Now we're going to look at an example. This is probably the only example we're going to get through. My suggestion would be that you go to my webpage and get the proof that's on the webpage off of there. And then there's one extra example that's easy. But we're short on time today, so here we go. Example 1, and this needs a lot of room. No. Example 1, you're going to use your knowledge, your algebraic knowledge of finding the midpoint of a segment, finding the slope of a line, and finding the distance of a line using the distance formula, and also finding lines that are perpendicular using slope. So we're going to use all of that here. So example 1, I want you to create an x and y axis, mostly, listen carefully, of the first and fourth quadrant. So it's going to look like this. You're going to have to go up high enough to go 8 on the y-axis, but 12 on the x-axis. So I would draw this. And you only really need to go 1, -1, into the fourth quadrant, so it's really not much of the fourth quadrant. So your coordinate grid axis is going to look something like that. Then I'm going to give you the vertices of a triangle. So triangle SGB has vertices S, which is 4, 7, G, which is 6, 2, and B, which is 12, -1. Please plot those ordered pairs and connect them, they'll make a triangle. you're going to see that you've created a very obtuse triangle. All right, so here's the first question. I'm going to put question A up here over to the upper right, so that we have, because both questions take some room here. So question A is asking you to find the coordinates of point J on segment GB, so that segment SJ is a median of the triangle. We'll talk about what that means in a minute, but that's going to be your question. They won't have graphed that for you. You'll have to graph it yourself. So it's imperative that you graph the point so you can see what we're doing. They're asking you to put point J on segment GB. Isn't this segment GB right here? So J is somewhere here, so that wherever J is on here, it connects to S and makes a median. You need to go back to your definition. What are the two characteristics of a median? Characteristic number one is what? Look at your definition of median. Comes from a vertex and goes where? To the side opposite's midpoint. Are you able to find the midpoint of a line segment in a coordinate grid? Don't we have a formula for that? If you don't know the formula, it's in your notes, but we're going to write it here again. So, write yourself a note that you have to find the midpoint of segment GB. That's our job, is to find that midpoint. Because we have to put J here so it's a midpoint, because it's going to connect with S, make some median. You can't eyeball it. You could if it were a vertical or horizontal line, but we can't here, it's diagonal. So the midpoint formula looks like this. X sub 1 plus x sub 2 divided by 2, comma, y sub 1 plus y sub 2 divided by 2 makes an ordered pair, an x and a y ordered pair, right? So we are going to find the midpoint of segment GB. So I used a little sub MP to say that we're finding the midpoint of this line segment. And so I'm going to just use that formula. And I'm going to go down to my ordered pairs down here. And I'm going to call G's point x sub 1, y sub 1, and B's point x sub 2, y sub 2. You can have them in reverse order, that's fine. But then I'm going to take my x's, aren't my x's 6 and 12, and put them here. And my y's are 2 and negative 1, and put them here in that formula. All you're doing is averaging the x's and averaging the y's. And so we get an ordered pair. What's 6 plus 12? Everybody? I know you know how to add. What is it? Thank you. Divided by 2? 9. What's 2 plus a negative 1? 1. 1 is not divisible by 2, so leave it as a fraction. It's the fraction 1/2, isn't it? And you might actually get a fractional point. That's possible. So please plot that ordered pair and call it J. So go to the right 9, 2, 4, 6, 8, 9, and go up a half. Isn't that on segment GB? If for some reason your midpoint doesn't land on the segment that you're trying to find the midpoint of, what does that tell you? You did something wrong. Go back and check your work. So it has to land on the segment, and it has to appear to cut the segment in half, doesn't it? There's my J. Please connect S to J with a dotted line. Now, we've found the coordinates of point J, and you can see that that's a median. Comes from a vertex and hits the opposite side of the midpoint. All right, part B to this. I'm going to do below. Part B is a little bit more tricky, but it's easy work. I want you to look at this. So point M, M is in Mary, has coordinates, write this down, 8, 3. So why don't we plot that on the triangle? Plot 8, 3. 2, 4, 6, 8, 1, 2, 3. Oh, oddly enough, there's point M. It sits on one of the sides of my triangle. Here's their question. Is segment GM, so segment GM would be from here to here. Is segment GM in altitude? You can't just say yes or no without any work. Is an altitude of the triangle. Triangle SGB. What do we know about altitudes? They what? They don't go up necessarily. This one doesn't necessarily really go up-ish. Look at your definition for an altitude. What are the two characteristics? Okay, let's start with the first one, though. The first one is that it comes from a vertex, right? Is one endpoint of the segment at a vertex? Yes. So far it meets characteristic 1 of an altitude. It comes from a vertex. And now what's the other one, Amanda? It's perpendicular to where? The side opposite, right? Side opposite is SB. We have to figure out, is this segment GM perpendicular to this segment SB? How do I determine if the two lines are perpendicular? Slope. You're not allowed to use a protractor to see if the angle is 90, but we can use slope. Don't we know something about slope of perpendicular lines? Yes. What is the slope of perpendicular lines? They're reciprocals and opposite signs. So here's your job. You need to find the slopes of segment GM and segment SB. If they are opposite signs, ignore that, and reciprocals, then the lines are perpendicular. Okay? So let's go ahead and find the slope of those two lines. You could use the slope formula, couldn't you? I know it's low, but I'm trying to keep the picture in there as well. Couldn't you use the slope formula? M is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. But you have a picture of the lines. Wouldn't it be easier to do a rise over run, make that stair step? Remember that slope equals rise over run. So I'm going to create a stair step above or below the line. So look at GM. Can't I make a stair step from here to here? Make a right triangle stair step? The rise is always up and down. So what rise from G to here? Is that how many places? 1. And it's a positive 1, isn't it? Because we're going up. And then to the right, how many places? 2. So the slope of GM, I'm going to use a sub M. Doesn't M represent slope? Isn't it a rise of 1 over a run of 2? So what would be my perpendicular slope to that? Negative 2. So let's find the slope of SB using the same method. SB. So from S to B, I want to make a stair step. So it's going to be a big one. You could do above or below. How far up? 8. And isn't this a positive 8 because we went up? Now we're going to the left. Left is negative, and isn't it 8 again? So we have our rise is positive 8 over our run is negative 8. What does that reduce to? -1. They were opposite signs, but not reciprocals. We needed it to be -2. So is this an altitude? No. So your answer has to be no. GM, segment GM, is not in altitude because the lines are not perpendicular. The rest, I want you to go again to my webpage and get the last 2 pages of notes. It's really just a proof and a real simple example.